Hi, I'm Ray Caramelli. I'm an IPC Master Instructor for STI Electronics. Over the last few years, there have been a lot of changes in our industry. A lot of these changes have come with the introduction and development of new components and the transition from tin lead to lead-free solder. With all these changes, some of our old methods just don't work the same way they used to. Also, some of our chip components continue to get smaller and smaller and smaller. This makes them much more difficult to remove and replace. Then we have devices with large center grounds, like DPACs and BTCs. These can be quite challenging. We also may have issues when we have to remove the excess solder from BGA LAN patterns after the BGA has been removed. This can be frustrating. During this video, we'll be demonstrating and discussing advanced hand soldering techniques that will help you meet these challenges.
Today's solder technicians are well trained. They know how to select the proper size tip for a particular soldering operation, and whether that connection requires a conical or chisel tip. They know about tinning the tip and the range of soldering temperatures required for the different solder alloys. And they know the importance of using a solder heat bridge to make an acceptable and reliable solder joint. On a daily basis, our solder technicians use these methods for the hand soldering of components that can't be soldered using wave or reflow soldering machines, and for performing rework of components that need replacement or touch-up. In this program, we'll be examining the advanced hand soldering techniques that will assist you in dealing with components and soldering situations that are less common. These topics include drag or multi-lead soldering, removal and replacement of ultra-small surface mount chip components, hand soldering methods for diode packages or DPACs, as well as bottom termination components or BTCs, heavy thermal mass through-hole components, and techniques for wicking solder from large BGA LAN patterns during site preparation. For each of these topics, we'll discuss the problems that occur when you use the tried and true methods, and then demonstrate how the advanced techniques will make your job easier and provide much better results. Prior to the discovery of drag soldering, the method of hand soldering high lead count gull wing components, such as QFPs, was to use point-to-point soldering. Not only was this technique rather tedious, it would take forever and make the rework operation very expensive. Drag soldering makes this rework process much faster and more efficient. A single-sided chisel tip is used to melt solder into a whole row of connections in one continuous motion. Let's review how this works for tin lead solder applications. We start by aligning the part to ensure that the leads are centered on the lands. Then, we tack two diagonally opposite corner leads. After the leads have been tacked, it's important to inspect the alignment in case it's shifted during the tack operation. After two opposite corners are tacked, select a row of leads that was not tacked and apply liquid or paste flux to the leads. Flux is critical for the drag soldering operation because it reduces the surface tension of the solder, so there's a reduced chance of solder shorts. Now we're ready to prepare the tip. First, make sure that the tip is properly cleaned. Next, we'll need to add some fresh solder to the tip. Then, position the tip against the first solder joint on one of the corners that is not tacked. When you have two corners tacked, it's critical that you don't start the soldering operation on one of the tacked connections because the position of the component may shift. As the tip moves from one joint to the next, the required amount of solder will transfer from the tip to the leads if you move at the right speed. You should be able to watch each connection form as you proceed. When you come to the end of the row, just keep moving the tip past the final lead in a continuous motion. If you stop the movement of the tip at the end of the row, you may end up with too much solder on the final lead or even a solder bridge. We then repeat this operation for the remaining rows of leads. When our industry transitioned from tin lead to lead-free solder, many solder techs began to feel that drag soldering was no fun anymore, that it had become a real drag. That's because using the technique with lead-free solder tended to produce multiple solder bridges. Given that we had to rework all these solder bridges, were we really gaining anything by using multi-lead soldering instead of point-to-point soldering? The good news is we have a technique that will make it less frustrating to perform drag soldering with the lead-free alloys. This new method reduces the possibility of solder bridges. The idea is to place the soldering iron tip out at the toes of the gull wing leads as we perform the drag soldering operation. Watch how beautifully this process works. Notice that the ball of solder on the tip should contact the lead and land, while we try to avoid any direct physical contact between the leads and the soldering iron tip. Make sure you're not too heavy-handed, or the tip may pull and bend the leads, and can actually remove a land. If you do create a solder bridge anywhere along the row of leads, you can just stop and reflux the bridge. Next, clean off any solder from the tip onto a damp sponge. Then reposition the tip on the bridge and remove the excess solder by pulling the soldering iron away from the body of the part. This is called the draw-off method. Another effective technique is termed the respread method. Ray calls this walking the dog, meaning he uses the soldering iron tip to move the bridge down the row of leads, sharing the solder with multiple leads until it is gone. Removing and replacing ultra-small passive components like chip resistors and capacitors can be a real challenge. That's because these components are really tiny. The smallest being 0.01 inches long and 0.005 inches wide. When we compare that to a standard size chip resistor, which is 0.08 inches long and 0.05 inches wide, there is a big difference. This means we'll need greater magnification to see the soldering operation clearly, and we'll need tools that are appropriate for the size of the devices being soldered. Let's review the standard techniques for removing an 0805 chip resistor using either a bifurcated tip or thermal tweezers. We'll start with bifurcated or forked tips attached to a standard soldering iron. After fluxing the component, we're ready to prepare the tip. Since this particular tip has a cavity, it will require special cleaning and tinning procedures. First, we'll need to remove any solder from inside the cavity of the heated tip. After cleaning the tip, the next step is to remove any oxidation and scale from the tip by adding solder to the tip and then removing it using a brass wiping pad or moist sponge. Now it's time to add solder to the properly cleaned tip. We need to fill the cavity up until there's a small crown of solder that reaches from one side of the tip to the other. We want enough solder to help transfer the heat quickly, but not enough to fall out of the tip cavity. The solder will also provide surface tension to lift the component off the lands after reflow. Since the tip has more metal surface area than the lands on the circuit board, the component will be drawn toward the metal tip. Bifurcated tips can be used to remove a number of different styles of chip components as long as the component will fit properly in the cavity. Unfortunately, bifurcated tips are not available for any chip components smaller than 0201. Using larger bifurcated tips won't work as well and may interfere with adjacent lands and components. Another common method for removing standard chip components is the thermal tweezers. In 1 or 2 seconds, you should see the solder melt. After you're sure that both joints are molten, lift the component straight up. Thermal tweezers are not small enough for some of the smallest chip components. Another issue with thermal tweezers is that as the tips get finer or sharper, those fine points are difficult to maintain, especially when using lead-free solder. The fine point tip geometries degrade faster since the plating is thinner on these points. Probably the best solution to removing these tiny components is to use a chisel tip that is sized so it will allow us to heat both terminations simultaneously. Then, after solder melt, we simply wipe the part away with the soldering iron tip, relying on the surface tension of the solder on the tip to remove the part. Once our ultra-small chip component has been removed, it will need to be replaced. Again, a change in technique will be required for the hand soldering operation. Let's review the replacement procedure for a normal-sized chip component. The idea is to add enough solder on one land to create a slight crown shape. We call this the solder prefill or solder bump method. With the solder bumped on the land, we're ready to align the component in the correct position. You'll notice that the pre-filled land will lift the component off the board slightly. Next, we need to add flux to remove any oxidation that will be formed during the resoldering process. Now we'll hold the component in position with a wooden stick or tweezers so that the soldering iron won't push the component out of alignment. When we apply heat to the pre-filled land, the solder will melt and the component will drop down onto the land. The solder should wick up onto the termination and form a fillet based on the amount of available solder from the prefill. Then we remove the tip and wait 1 or 2 seconds for the solder to solidify before we remove the holding tool. Now we can solder the other side. The tip should contact both the land and the termination while the solder is added to the opposite joint. Be sure to add just enough solder to form a proper fillet. You can use almost any style of tip you prefer for either soldering operation, chisel or conical. Keep in mind that it's best to use the largest tip possible to transfer heat as quickly as you can without touching the board or any adjacent solder joints. What's different about hand soldering the ultra-small components is that trying to bump only one land is more difficult and may result in a bump that is too large for an effective solder bump. Instead of using solder to pre-fill one side, we'll use a blade tip or mini wave to do pad re-leveling, so there will be a fairly consistent solder bump on both of the lands. After we flux the solder bumps, we place the chip component alongside the lands. Then, we bring in an appropriately sized soldering iron tip so that the tip barely touches the sides of the bumps. This placement will cause the bumps to melt. While the bumps are molten, slide the component onto the lands, allowing it enough time to wet properly. When this is done correctly, the edge of the soldering iron tip can be used to help align the component. Be aware that the biggest problem when hand soldering ultra-small chip components is handling the components. This is because even tweezers with the finest points will dwarf some of these components. Diode packages and bottom termination components are distinguished by a center ground on the underside of the component. In addition to the center ground, D-packs also have gull wing leads. BTCs have leadless terminations on 2 or 4 sides of the component. Examples of BTCs are dual flat no leads, or DFNs, quad flat no leads, or QFNs, and leadless chip carriers, or LCCs. LCCs have recessed terminations called castellations. Now let's examine the steps for hand soldering a D-pack. First, we'll preheat the circuit board assembly. Preheating will help to ensure that the large ground termination will be easy to solder with a soldering iron. We want the board temperature to reach 100 degrees C for tin lead solder or 150 degrees C for lead-free solder. At this point, we're ready to solder. Now, we apply flux to the ground termination land on the board. Next, using the largest soldering iron tip available, typically a blade tip as wide as the termination, we flow solder onto the ground termination, forming a solder bump. After cleaning the flux residue, we apply more flux to the ground termination solder bump. Then we place the D-pack component so it's aligned with the lands on the board. The ground termination of the device will be slightly raised since it is resting on the solder bump. Next, we use a wood stick or tweezers to hold the D-pack in place and apply gentle pressure. Now lay the blade tip of the iron across the width of the land on the edge of the component. This will cause the solder bump to melt. At that point, the gentle downward pressure of the holding device will settle the ground termination of the D-pack against the land. Finally, we solder the remaining gull wing leads using conventional hand soldering techniques. This method of hand soldering D-packs often provides a better soldered termination than an automated process. With an automated process, the D-pack is placed on solder paste deposits and then gets processed through a reflow oven. It's quite common for the ground termination to have voiding present because of the inability of the volatiles in the paste to find an escape route from under the ground termination of the device. These voids can affect heat dissipation and may make the connection less reliable. When hand soldering, there are less volatiles to escape, and the pressure applied to the component ensures intimate contact and squeezes out many of the voids that may form. Now that you understand the hand soldering techniques required for the D-pack, let's turn our attention to BTCs. Hand soldering BTCs can be a little more complicated than D-packs. For our example, we'll be soldering a QFN that has a center ground and a single row of outer perimeter terminations on all four sides. We'll start by applying flux to the center ground termination land on the circuit board. In the same manner as the D-pack, we flow solder onto the ground termination to form a solder bump. Then, we place the QFN in its proper position, so that pin 1 corresponds to the pin 1 location on the circuit board. Now, we make the appropriate adjustments so that the terminations are in alignment with the lands. The device will be slightly raised since it is resting on the solder bump. Next, we use a wood stick or tweezers to hold the QFN in place and apply gentle pressure. At this point, we use a hot air system to direct heat to the component area. This will cause the solder bump to melt. The gentle downward pressure of the holding device will settle the ground termination of the QFN against the land. Make sure that the outer perimeter terminations remain aligned with the lands. Then remove the hot air heat source and continue to hold the device in place until the solder has solidified. This QFN has outer perimeter terminations that can be soldered with a hand soldering iron. You can use point-to-point soldering to complete the job, or in many cases, you can use the speedier drag soldering technique. Certain bottom termination components cannot be hand soldered because some of the terminations are not accessible on the perimeter of the component. In these cases, soldering will have to be accomplished using a rework station. Large through-hole components with heavy thermal mass provide challenges for hand soldering. As you can see, this component is difficult to solder because it needs more heat to achieve proper wetting. The tendency is to raise the soldering iron temperature, but higher soldering iron temperatures can result in lifted lands, overheated solder, and circuit board and component damage. The answer is to use auxiliary heating to preheat the assembly. Preheating makes it easier to solder a connection that requires more heat. Preheating means you won't have to raise the tip temperature to achieve proper wetting. Let's watch this comparison of soldering a heavy thermal mass component with and without a preheater. Our final topic involves site preparation for large BGA land patterns. For example, it could take forever to remove solder from each land of a 500 ball array, one at a time, while using wicking braid. The most efficient method of clearing solder that has been unevenly distributed on the lands after the BGA has been removed is to use a combination of a large blade tip and a solder wicking braid. Before we examine this procedure, let's take a look at the risks and benefits of two other options: handheld extraction and automated solder scavenging. Using a handheld vacuum extractor with a special tip, a solder technician can manually run the tip across the BGA lands to remove the excess solder. This technique works, but there is not much control in the process. An unskilled operator can actually suck lands right off the board. Also, this method is relatively slow. Higher-end rework stations have automated scavenging systems. The advantage to this type of system is that it is non-contact, meaning that nothing physically touches the board. In other words, there is no risk of lifting lands. Now, let's examine the technique we recommend. As we stated earlier, this technique involves using a large blade tip and wicking braid. If we tried using wicking braid to remove all the solder, we'd consume quite a lot of braid and the process would be slower. The blade tip allows us to pick up the bulk of the solder before using the solder braid to complete the operation. It is best to do this manual wicking operation while the board is still hot from the BGA removal process. After BGA removal, liberally apply paste flux to the BGA lands on the board. Next, select a blade tip that is large enough to span the width of the BGA land pattern if possible. Slowly, with no pressure, glide the clean, dry tip across the land patterns. Notice that much of the excess solder will accumulate on the tip and then can be wiped off on the sponge of the solder station. Notice that there are now fairly consistent solder bumps on all the BGA lands. At this point, we again liberally apply paste flux to the lands. We also apply flux to this very thick wicking braid made especially for BGAs. The flux on the braid will help provide a better solder flow onto the braid. Now, we lay the wicking braid down across one edge of the entire BGA land pattern and bring the blade tip down on top of the braid. As the solder starts to melt and flow into the wicking braid, slowly glide the blade tip and the wicking braid across the rest of the BGA land patterns. Notice that we never use any pressure when using the wicking braid. If you feel any resistance, make sure you stop to reduce the risk of damage to the lands, such as a lifted land. If the blade tip is not wide enough to cover the width of the land patterns, we make several passes until all the lands have been wicked. The last step is to clean the flux from the site. Then we're ready to perform the BGA replacement operation. If the BGA will not be replaced soon, we store the board with the solder bumps on the lands, waiting to perform the wicking braid operation until we're ready to replace the component. If we completely remove the solder from the surface of the land, what is left is a thin layer of inner metallics. These inner metallics will oxidize quickly and leave an unsolderable surface. That's why we don't do the final solder removal operation until we're ready to do the BGA replacement. This program has presented some advanced soldering techniques for the challenging situations you'll find yourself in when working with many modern components. We demonstrated the modified methods that can be applied to drag soldering, removal and replacement of ultra-small surface mount chip components, hand soldering DPACs and BTCs, working with heavy thermal mass through-hole components, and for wicking solder from large BGA land patterns during site preparation. All it takes are the right tools and the right techniques and lots of practice. Remember that these advanced techniques require a higher skill level, so it will be necessary to practice until these skills are built up to the appropriate level. In this manner, you'll produce high-quality solder connections and will be able to take pride in a job well done.